Hi, my name is Thijs.
And I'm Marianna.
And welcome to the third and final part of the video series about Varnish Enterprise's massive storage engine. Did you miss out on episode 1 or 2? Don't worry, they're linked in the right upper hand corner. They will take you directly to either episode 1 or episode 2. In part 3, we'll focus on the limitations of the operating system's kernel and how MSE's implementation can cope with that. From re-implementing the page cache mechanism in user space, to designing cache stores with file system-like behavior that avoid disk fragmentation, to even an improved disk LRU mechanism. We'll also talk about memory bookkeeping and about the optimizations we do by using journaling, and we'll end the entire series with a quick recap and a glimpse into the future.
The kernel assumption can become a bottleneck for Varnish. The kernel's internal page cache size is a good example. The kernel will store items in its internal page cache using chunks of 4 kilobytes, which means that whenever we insert an object in cache, this object will be most likely fragmented in different chunks. And whenever we will need to deliver this object, we will have to collect and aggregate each of those fragments. And this leads to a lot of I/O operations, which might be detrimental for performance at large scale. That's why with MSE, we have re-implemented this logic in the user space, bypassing the kernel's limitation. And we can now define how big we want the memory chunk to be. And by default, it will be a 4 megabyte chunk. Another potential bottleneck is the overhead that memory bookkeeping generates in the kernel. For systems with a large number of objects in memory, this can be tens of gigabytes of memory overhead. And that's why with MSE we have re-implemented this in the user space, because for products like Varnish Enterprise, memory is a valuable resource.
Another level of bookkeeping optimization is the journaling that is done on the metadata database that we call the book. When large amounts of transactions happen, we don't want I/O operations on the book to become a bottleneck. Instead of waiting for the completion of a consistent state, we write changes to a series of journals which will eventually be synchronized with the book. In future versions of MSE, we will even increase the amount of journaling that is done. A regular file system is not optimized for caching. It thinks in terms of files and directories rather than cache objects. Instead of storing persistent cache objects on the regular file system and letting the kernel deal with it, we designed our so-called stores to have file system-like behavior without actually being a full-blown file system. MSE stores can live on a standard ext4 file system. However, the massive storage engine doesn't want to deal with the limitations of directory traversal or the overhead of opening files. That's why MSE version 3 pre-allocates a single large file per store where all the objects are kept. Each file is only opened once, and because there's only a single pre-allocated file per store, disk fragmentation is heavily reduced.
Another way MSE3 reduces disk fragmentation is by implementing its own optimized LAU algorithm for persistent objects. The regular LAU will remove the least recently used objects whenever space is needed in cache. This makes it, of course, an on-demand and iterative process, which requires a high number of I/O operations and can lead to disk fragmentation. On the other side, MSE3 continuously removes objects from the lower third of the LAU list until the occupied space is below the configurable high water level. This is done by a series of linear LAU evictions, which keeps track of where they ended. This avoids spending computing time on objects that weren't suited in the very first place. And of course, we do now have higher chances of finding neighboring free space, which reduces disk fragmentation.
What does the future hold for the massive storage engine project? In future versions of MSE, we'll add more journaling to further reduce the I/O operations and making MSE even faster. We'll add a granular LRU configuration that allows you to influence the behavior of the LRU eviction mechanism. And finally, we'll provide a VCL interface that allows Varnish Enterprise users to control which objects are persisted to a specific store. After having heard all of this, why would you want to go for the massive storage engine instead of combining the out-of-the-box memory and file stevedores that come with Varnish? Let's recap. If you combine regular memory servers and regular file servers, you will not benefit from a shared cache. If you use the standard file stevedore, disk fragmentation will occur. If you use the standard memory stevedore at very high concurrency, LRU memory hijacking may occur. Because of its optimizations and its design, MSE is faster and will trigger less I/O operations. And because the massive storage engine can persist objects to disk, whereas the regular file stevedore can't, you'll have disaster recovery and cache pre-warming. So if you're looking to cache a massive dataset, the massive storage engine is exactly what you're looking for, whether you're building a custom CDN, accelerating a video platform, or a high-traffic website or API.